Hello everyone, this is Haneen Al-Suradi from New York University. Today I'll be presenting our work on detection of tactile feedback on touchscreen devices using electroencephalography or EEG data. Conventionally, haptic experiences are evaluated using subjective measures such as self-reporting. EEG, however, has a potential to provide a deeper insight into the haptic experience. So in this study, our objective is to detect tactile feedback on touchscreen devices using EEG data. This is the protocol of the experiment. The experiment was done using Tanvas touchscreen device, which is capable of providing friction-based tactile feedback. Subjects had to move their right hand index finger across guitar strings shown on the screen of the device from top to bottom. For each trial, tactile feedback was either enabled or disabled randomly. If the tactile feedback was enabled, you will be able to actually feel the guitar strings when you swipe your finger on the screen. 26 subjects participated in this study, which was conducted under two conditions, with or without tactile feedback. Each trial was repeated 96 times, and data was recorded from 58 channels. For each channel, the power spectral density of beta band was calculated. This data will be used to perform classification. This block diagram shows the implementation of the pre-processing steps highlighted in red and the classification steps highlighted in green. Once data is pre-processed, we feed the data to the classifier block. We start by the feature selection, which is simply dropping the EEG activity before the onset of the experiment, simply because it doesn't help in classification. Then we selected 4 brain regions and averaged the activity per region. In the figure, you can see that frontal and somatosensory regions are selected. We use support vector machine classifier for each region. We performed a 10-fold cross-validation training and we selected the best performing brain region. Next, we selected the best performing 3 channels within the selected region. To enhance accuracy, we implemented data augmentation, which is basically trying to populate the training data from the existing ones by time shifting each of the activities slightly to the right and slightly to the left. This helped us to triple the training data size. Lastly, we implemented a voting classifier out of the selected channels. Here, we list the results. You can see that using the middle frontal region yielded the highest accuracy of 68%. Using the best performing channels within this region enhanced the accuracy to 73%. Another boost of accuracy came after implementing the data augmentation and implementing the voting classifier, which increased the accuracy to 85%. We would like to thank NYU Abu Dhabi PhD Fellowship Program for supporting this research. Thank you so much for listening.